KnectIQ is like Microsoft in that we also care about these types of app migrations, and we assist in these migrations. Unlike Microsoft, we're considerably smaller, and we focus primarily on just one thing, which is the securing of data in flight. I'm going to just pop my webcam off real quick and continue. So what we're going to talk about today is certainly migrating applications, but we're going to focus on just that security aspect of it. Okay. Let me flip here. When you migrate apps to the cloud, the reason that, or when you're in a sort of partially migrated state, you're often going to find yourself where you're using apps that were written, before internet security was a big, it was well addressed. The protocols that we're going to talk about in today's talk about how we secure data in flight were invented actually after mainframes, right? But a long time ago. And so it's this weird case where we're talking about, potentially old mainframe architectures. We're talking about semi-old, relatively speaking, security protocols. And then we're talking about, the modern day and what we can do to make sure that the way that we move into these cloud or hybrid cloud, hybrid cloud on-prem environments, how we do that securely. So legacy apps are vulnerable because they were oftentimes written before TLS was commonly used to secure those. But nevertheless, cloud migration is happening, especially with workers working at home. Security is super critical, right? And I just put up a very simple representational drawing of what we're talking about here, where you could end up with an on-prem data center app needing to communicate with an app that's already migrated to the cloud. Maybe both of them are being accessed from home settings. And how do we make sure that this communication that goes between those different locations is secure? So as we talk about how to solve that problem, I want to talk about specifically what isn't the problem with this. And specifically, the problem is not encryption, right? The encryption algorithms that we have today are very strong. The problem is more how you use encryption. And encryption works like a lock, right? Where if I have a key to the lock, even if it's a very strong lock, I can still open the lock because that's what the key is designed to do for the lock. And in broad speaking, encryption works the same way, right? If I have a cryptographic key, I can decrypt data, I can encrypt data with it. So the problem is more the keys than the encryption algorithms, and that's what we're going to address in this migration, because again, that is the vulnerable spot when we're talking about this communication. I'm specifically going to talk about how data communication is secured today with respect to HTTPS or TLS. Or SSL actually is what TLS came out of, and that's how most data in flight is secured today. It also applies to other data in flight protection schemes, but for the sake of just kind of walking through one specific example and the vulnerabilities that are associated with it, we're going to focus on TLS. And the way that works is you've got a key pair at one end that's used to negotiate a pair of keys, one at the sending side and one at the receiving side, and it's the same key. And remember, encryption works like a lock. So with that key, I can encrypt the data, send the data to the receiver, who can then decrypt the data. And we call it secure, not because we don't think that there are bad actors on the internet who might be able to intercept that data in flight. In fact, we think the exact opposite. When you think about all the certifications that we get for our data centers and the security that we have, it's because we know that there are so many bad actors, and a simple look at the news lets us know this. I'm not going to belabor this because we all already agree to this. But it's not that they can't see the data in flight. It's that when they grab the data in flight, if it's properly encrypted, they cannot read it, right? So it doesn't do them any good to see the bits that are traveling across the net. So what's the problem? Really simply, and we kind of took our hat to this earlier in the presentation, the bad actor gets a copy of that key, they're able to compromise the data. Compromise just means really briefly, they can read it, they can change it, which is a problem if that data that you're sending back and forth is valuable. But it's not just this private key that exists on the receiver end that's a vulnerability in the system. The only reason that the sender trusted that key was that it was signed by a certificate authority. And in order for that to work, the sender has to trust all the certificate authorities out there. Now, it does this through some massive mathematical operations that we're not going to get into, but what that means is that there is a private key behind each of these certificate authorities that if the bad actor gets a copy of it, they're again able to compromise that data in flight. And it doesn't even stop there. One more example is oftentimes when people are using a computer from an office or even from their home through a VPN, they'll go through a content filter or an SSL intercept that scans all of their web browsing, for example, for malware, or maybe looks for data loss prevention. You know, are we sending data outside the company that shouldn't be sent? And in order to do that, it needs to decrypt the data in flight, which is, of course, what the bad actor is trying to do. But for the good guys, we want to enable that. So there's yet another key and certificate that's trusted by the sender machine that, if compromised by the bad actor, allows the bad actor to attack that data in flight. And this is all, again, right, for mainframe apps. You know, it may be possible that some of these apps have a very network-centric security model, and they aren't even using encryption. So we need to do something about it, because whether, I mean, certainly if we're not encrypting, but especially if we're using the system that I just described, we're using a system that is vulnerable to literally hundreds of single points of failure. And to be clear, I'm not misspeaking when I say hundreds of single points of failure. All that means is that any one of those hundreds of keys falling into the bad actor's hands enables the data in flight to be attacked. So that's interesting, isn't it? Because today we talked about high availability in the last presentation. We certainly want that in all of our production services today. And this is why we have redundant power. It's why we have backup databases, network connections, web servers, even redundant geographies, right? So that if one geography were to stop working, we could fail our services over to another geography and continue to deliver that. But it's interesting, I think, that when it comes to securing our data, we don't just have one single point of failure, but it's literally hundreds of single points of failure. And they're not all even in the United States. They are in certificate authorities around the world. And so when we trust that our data in flight that's secured using standard techniques is secure, we're also trusting that all those certificate authorities around the world are all doing a perfect job at keeping their private keys out of the hands of the bad actors who might attack this data. It sounds scary when you put it that way, and it is to some extent if you care that much about the privacy of your data. This is why, for example, the Department of Defense doesn't allow you to use this system for classified data. But it isn't just that it's more vulnerable, right? That you have the hundreds of single points of failure. The problem is you don't even know when any of these keys has been compromised, and so you can't tell who is decrypting your data. And the converse side, or the flip side of that same coin, is that we can't tell when our data is being attacked, when someone is trying to get access. And it's not to put too fine a point on it, but it's because these attacks are happening outside of our networks. They're happening in the shared networks of the internet, so we can't see whether they're happening. So we need something new. And doing something new is going to require us to have some new ideas. So I'm going to encourage you to strap on your thinking caps for a second here as we question authority. Who says we should question authority? Well, in this case, it's me, right? But this is a good thing to do, right? In computing, we can't continue to assume that the solutions that we used in the past will continue to avail us in the future. So before we talk about the solution, let me take a quick moment to discuss why things are so bad. And this is not a detailed analysis, but it certainly isn't the case that the people who built these protocols didn't know what they were doing. I worked at Cisco Systems for a number of years, and I worked alongside people who sat on these committees that developed a lot of protocols that are used to run and secure the internet as we use it today. And they're smart people, and they care deeply about what they do. So why are things so bad? I would suggest to you that the problem is not that they didn't do a good job, it's because they were solving the problem for a fundamentally different internet. because the internet has changed since the 1990s. I put a few images up on the screen just to give us some visual representation for that change, right? We have these AOL CDs that are giving us access to dial-up internet from our cutting-edge laptops. We can see that download times were oftentimes measured in the thousands of years back then. And the most actually informative part of this image is this graph in the background here that shows the, for lack of a better word, population of the internet. And it was doubling, literally more than doubling oftentimes every single year in the 90s when these protocols for securing our data in flight were created. So it shouldn't surprise us then that a protocol that was used to solve the problem then has changed. And the reason for that is that the problem has changed, and that the problem they were solving then was to secure communication for, relatively speaking, a large number of unknown entrants to the internet, because it was growing so fast, to a relatively speaking small number of well-known services. And so the system that they came up with solved that problem well. And it was implemented by these certificate authorities around the world, and it was fundamentally a security-first solution, right? Where if you had a key and a certificate that showed its authenticity, that proved its authenticity, excuse me, and you can tell that, right, by seeing that this lock symbol appears on the left side of your address bar of your browser, sometimes with the word secure, then you know you have a secure connection. Once you have a secure connection, the next step then is to prove your identity. And you do that by typing in your username and password, or if it's an API, maybe it's an API key and secret. But our observation is that today the internet has changed from, remember, the AOL CD thick laptop ages. And today when we share secure data, we're almost always sharing it with parties who we already know. And so what we would suggest is that it makes sense to use the identity, our knowledge of the other end's identity, to create better security. So let me quickly then walk you through how a system like this works. In this case, it is our system. I want you to pay attention to how we're eliminating the single points of failure so that it's ultra secure, how we are verifying the sender and receiver for every communication, which incidentally is a very zero trust principle, which is something that we're also heading to, which we won't get into deeply today. And finally, I'll call out later on in the explanation how this enables us to do real-time threat detection for our data in flight. So the first part is to identify the endpoints. And the way that we do that is by quote unquote pairing our endpoints with our service, right? So after pairing, it works kind of like a Bluetooth pairing, where after the provisioning, the endpoint recognizes our encryption service, loosely speaking, our trust environment service, and our trust environment recognizes that endpoint. We do it all without any static keys. This encryption here isn't just moving the problem that we have with TLS to a different spot, but we're actually rotating this crypto here, similar to a double ratchet cryptography, for those of you who are into the crypto side of things. And then once we've identified both endpoints, and it could be many endpoints, but for this drawing, it's just the two, then when we want to encrypt data to send between them, what happens is the sender, when it goes to encrypt the data behind the scenes, it causes key DNA to be downloaded to that sending machine. That key DNA, just to explain it really simply, is information or entropy that allows the sender to create a cryptographic key, which, as we discussed earlier, key is like a lock, right? It can encrypt that data. And then this is where it gets really different, is after that encryption, we immediately wipe the key from memory. Why? Right? We wipe it from memory because we don't need it anymore. The data is already encrypted. Keeping it around just leaves a threat surface that this bad actor can take advantage of to steal that key for future or ongoing communication. The data is then sent to the receiving end the way that it normally is. We're not doing anything to change the way that data flows in the system. We're just a control plane solution, which means that we're A, lightweight, and B, you don't have to do a lot to use this technology. And then on the receiving end, the inverse happens that happened on the sending end, right? Key DNA is again downloaded, That key DNA is used to create a cryptographic key, which is used to decrypt the data. And again, the key is wiped from memory because, again, we don't need it anymore. It's just a vulnerability after the data has been decrypted. The next piece of information that's sent from the sender to the receiver is going to use an entirely different key. We call this ultra secure because if the bad actor does intercept data, there's nothing that he could have stolen either before the data was sent or after the data was decrypted that would allow them to attack that data in flight. And even if they did somehow get into a machine's memory at one point, that would get them one piece of data. And when I say one piece of data, by the way, I just want to clarify, if we were encrypting this video presentation here, we wouldn't be using a new key for every single packet, right? We would use a key for a certain period of time, maybe 5 minutes, maybe 10 minutes, maybe a half hour, depending on the security requirements, and then we would rotate it. Ultimately, what this does is it provides you security, and then it gets rid of those hundreds of single points of failure. There's no dependence on the certificate authority system. We are verifying the sender and the receiver, right? Every time I encrypt or decrypt information, I'm fetching key DNA from the service, which is then logged, that allows me to see exactly which endpoint encrypted and decrypted every piece of information. We're doing real-time threat detection in that if any endpoint tries to impersonate one of the endpoints in a communication, or another attempt is made to access that key DNA that is unauthorized, we raise alerts in the system. And we move from a system where Zero Trust says that only authorized users are given access, and what we find out is with existing systems, it's actually anyone who has any of these hundreds of keys who has access, to a system where we are verifying that endpoint for every single cryptographic application. So it's very Zero Trust compliant. And it isn't just us that are saying that this is the way that we should be going as a country. The NSA released guidance just last month on Zero Trust, saying that, quote, in a traditional network, the user's credentials alone are often sufficient to grant access. But in a Zero Trust environment, the device is not known. So the device fails authentication and authorization checks, and so access is denied and the malicious activity is logged. I bring this up because I know what I'm saying here is requiring us to question authority, what we've learned as far as the acceptable ways of sending data back and forth. But what I'm telling you, and what the NSA is telling you here, is that in order to have security in the world that we're living in now, we need to move on from that. We need to be confirming that that device is the device that we think it is. We need to be using identity-first solutions. So what does this have to do, or how is this applied to mainframe applications? I'm going to go back to the same drawing that we had in the beginning, right? Again, we had multiple data centers, and this is actually an actual application story for us, right? We needed inter-data center communication. This, in fact, was a banking app, and so who likes auditing more than bankers, right, and finance people? And I say that jokingly, but it's actually security people too who love the auditing. And this particular client wanted to do it without having to change their code. And so what we did is we built a solution that allowed a proxy to be placed outside of the actual app at both ends. No code needed to change. All that needed to change was how that API call got routed to the other end. Instead of going directly over the internet on a fundamentally vulnerable connection, it went to this proxy instead, which wrapped it up on the one end, transferred it to the other data center in a secure and auditable way, and then unwrapped it and sent it to the application on the other end and allowed the response to go back. Simple technology, right? Easy to implement. This is a days, not weeks of work. This is a no code change implementation, but it provides you auditable security for all of this cross-cloud communication. And that is where I'll stop today.